Hello, welcome to CSC7013, Advanced Math for Computer Scientists. This is Brady Chen. Today, we're going to talk about Module 5, Binary System, and its application. This is Part 2. In Module 5, we're going to talk about how computers represent different types of data. Remember, in previous module, we just talked about a computer system consists of various different circuits, and each circuit is basically built upon a whole bunch of gates. Now, these circuits are designed to deal with binary numbers, and for all the data, eventually it will be converted into binary numbers and stored in the memory and processed by the computer CPU. So now, modern computer can represent various different types of data. For example, like the text, like the alphabet. Okay, and then we can also use the computer system to represent numeric values like integers and floating point numbers. And then in most of the modern computer system, you can actually represent some kind of multimedia data like sound, the music, and images or even videos. As was mentioned in the previous module, data can be stored in computer memory as binary digitals, though data are often viewed as the lowest level of abstraction from which information and knowledge are derived. Now, technically, data and information are different. Data refers to raw and unprocessed materials, while information is processed data. Information typically carries some meaning. Okay. Now, with the modern technologies, the text, numbers, pictures, audios, or even like videos, and nearly any other form of information can be ultimately converted into a string of bits, binary numbers. Okay, so that means we can store and process any data type in modern computer system because they can be converted into the string of binary bits. Now let's look at the simplest data type, the textual representation. A text document is normally decomposed into individual characters, such as the alphabet, numbers, and other symbols like the punctuation characters and the factorial, backslash, forward slash, and etc. As discussed earlier, the computer memory can only store binary digits. And now, how can we use these binary digits to represent different characters? Okay, so now before we do this, we need to first define or identify a list of all the distinct characters. Okay, we need to define these distinct characters. We call it a character set used in the document. Then we can represent each character with its binary digital code equivalent. Sometimes we call it bit pattern. Okay. So first we need to figure out what character set do we need to represent. Okay. So let's take a look at the simplest case. That's an example of an English document and list all the possible characters that the document may use. Okay, so we listed 3 items. The first, we need 26 letters, 26 alphabet from A to Z. Now, since we have to treat the lowercase and uppercase letters separately, so we have to also define the bit patterns for the lowercase letters. So that's total of 26 plus 26, right? That's total of 52. And also, we need to represent 10, numeric digits. Now, why we want to represent numeric digits? Because they are already digits. Now, remember, we only use binary numbers in the computer system. So now, the 10 numeric digits are basically digits defined in decimal. So we're going to use like a 0, 1, 2, all the way to 9. So now, for some of the symbols like a 2 or 9 or any letters between 2 and 9, there's no way you can represent in the computer system because computer system only use 0 and 1. So we need to define each of the digits used with the binary digital code. Okay. So then we also need to, map the other symbols such as punctuation character, factorial, backslash, forward slash, or even space character. So when we place the space bar, so it seems like you don't print anything, but space bar takes some space, so it's treated as a character as well. So these are the text representation. Now, how can we represent this? A well-known character set is called ASCII code. Now, ASCII code stands for American Standard Code for Information Interchange. Now, ASCII code was initially proposed by American National Standards Institute, ANSI, in 1963 and finalized in 1968. Now, the characters included in ASCII code are mostly the characters we can find on the computer keyboard. Basic ASCII code represents characters as 7 bits. So people use 7 bits to represent an ASCII code. That's the basic ASCII code. They use 7 bits. Now remember, in the previous module, we know that if we have 7 bits binary numbers, then we can map to a decimal value, right? So now the first question is, with 7 bits, how many different numbers we can represent? Okay, so let's think about the problem this way. So suppose that if we put all 0 in these 7 bits, okay, now we know that we can convert this 7-bit binary number to a decimal, which is 0, right? We know how to convert between binary and the decimal numbers. Now, and then we can continue to count the number, like if we put the 0, 0, 0, 0, 0, 1, that's basically maps to 1, okay? And now we can continue to, write the next value, which is 2, 0, 0, 0, 0, 0, 1, 0. Now, what's the largest number we can represent with 7 bits? If we put all 1 here, right? So then we can convert into a decimal value. And what's this decimal value? If you still remember how we convert a binary number into a decimal value, we know that this is 1's position, and that's 2's position, 4th, 8th, 16th, 32, 64. Because the value at each position is 1, so then basically we can add all these numbers. So that's 64 times 1, 32 times 1, 16 times 1, 8 times 1, and 4 times 1, 2 times 1, 1 times 1. And we'll find out this gives you 127. So with 7 bits, you can represent, 128 different characters, right? From 0 to 127. That's total of 128 different numbers. Now, if each number maps to a character, that's total of 128 characters. Okay. Now, if you count the characters on the keyboard, that's pretty much the numbers we're talking about. Maybe fewer than 128. Now, the standard ASCII code was later extended to an 8-bit pattern called the Latin 1 extended ASCII. Now, why we want to do this? Because people want to define a big character set, a set that contains more characters. Now, the reason for this is because sometimes they want to include more symbols, such as non-English letters like French, Italians, or even Russians, or something like this. Or we want to add some mathematical symbols. Okay, so now with 8 bits, the standard ASCII extended to the Latin 1, which is 8 bits. Now, how many different values we can represent using 8 bits? Again, we can check what's the smallest number you can represent with 8 bits. 0, 0, 0, 0, 0, 0. That's the smallest number, which is the same as 1. What's the largest number we can represent with 8 bits? 1, 1, 1, 1, 1, 1, 1, 1. And then we find out you can actually get 255. Okay. So the total number character we can represent is 256. That's double the number of 128. Okay. So this is one reason why we want to extend the standard ASCII to 8-bit extended ASCII, or the Latin 1. The other reason people want to use the 8 bits is because most computers manipulate data in 8-bit bytes. Because 8 bits actually is the power of 2, which is 2 to the 3. And now, for most of the computer system, now the memory can be divided into a small unit called a cell, and each cell is 8 bits. So for 8 bit, you can actually store one ASCII code into one memory cell. So that's very convenient. Okay. Now, this is a Latin 1 extended ASCII code, because it contains 8 bits for each character. However, the table only shows the first 128 characters. It doesn't show the characters from 129 to 256. Now, it's extended ASCII code because it used the 8-bit binary bits to represent each of the characters. Now let's take a look at the English letter A. Okay, so let's first look at the capital A. So that's capital A. Now the corresponding ASCII code is 65. Okay. Now the binary code is 0100000001. Okay. Now B is actually the character next to A, so the ASCII code is actually 66, which is one more than 65. And the C is 67 and D is 68. So if you look at the English letters from A to Z, you can see that the corresponding ASCII code actually increase. Okay. Now the lowercase English letter A to Z actually start from 97. So A is 97 and the Z is 122. Now let's take a look at another example, like a plus, which is 43, factorial 33. So this table is actually kind of complete. Now here's an example of ASCII code. Now using the ASCII code, we can represent any string into an ASCII code. Okay, so for example, let's take a look at this 6-character string. Hello. Okay, and it contains 6 characters. The first one is capital H, lowercase e, L, O, and factorial. Okay, now to find out what is the ASCII code, the computer system is going to use, we need to check the ASCII table, right? So what is capital H? And then if we go back and check the ASCII table, we will find out the 8-bit pattern is actually 01, 001, 000. Okay, that's H. Okay, and then the ASCII code for E is 011000101, and L, another L, so they have the same ASCII code. Okay, O, and that's factorial. Okay, that's 01000001. Okay, so that's the actual code, which is actually stored in the computer memory. So that's an example of ASCII code. Now here's another character set. It is called a Unicode. Unicode is rapidly gaining popularity because the traditional ASCII code can represent up to only 256 characters, even if we use the Latin 1 extended ASCII code. Now, with 256, you can represent only Western scripts such as English, French, and the German languages. Now, the Unicode use 16 bits instead of the extended ASCII code, which use 8 bits. Now, Unicode use 16 bits. Now, with 16 bits, how many different characters you can represent? You can represent 2 to the 16, which is 65,536 characters. Now, this is enough to store most of the world's characters. And you can store the characters like Chinese, Russians, and many other language. And also you can represent some special symbols. Okay. So Unicode can be implemented by different character encodings. Now the most commonly used encodings are called UTF-8, okay, which was designed to be the natural extension of the extended ASCII code. Okay, so which means that the first of 256 characters in Unicode character set correspond to the extended ASCII character set. Okay, so it's kind of backward compatible with the extended ASCII code. This is good. Now it's your turn. Suppose I have the following message encoded in 8-bit extended ASCII code. Now, what does it say? So I'm going to post this on the Blackboard, the discussion forum. So you can actually, look at the ASCII code table and try to encode this message. Okay. Now let's look at another data type, the numeric value. A numeric can be represented and stored in computer in two different formats. The first one is the binary notation, as was discussed in Module 4. And the other format is the ASCII characters. Now let's take a look at the example. Let's look at the number 49. Now if we treat 49 as the binary notation, then we can basically directly convert 49 into a binary representation, which is 110001. Now if you want to actually put this binary notation in 8 bits, then we can add 2 zeros to make it 8. Okay. Now you can also use the tooth complement representation. Right? Now for tooth complement, if 49 is a positive number, so the tooth complement representation for 49 is the same as the binary notation. If we try to represent a negative number, then the tooth complement notation is much better. Okay. Now another way to represent 49 is to use ASCII characters. Now we treat 49 as a string, so which contains 2 characters. One is 4, the other is 9. So we can find the ASCII code by looking at the ASCII table. Now we find out 4 can be represented using the ASCII code of 00110100. Okay, now look at the ASCII table. We find the ASCII code 9 for 9. Okay, it's a 00111001. So 49 can be represented as the 8-bit sequence and another 8-bit sequence. So we use total of 16 bits to represent 49. Now if we want to use the Unicode, which typically use 16 bits for each character, now if we treat 4 as a Unicode, then 4 we need 16 bits to represent 4, and 16 bits to represent 9. So then we need a total of 32 bits to represent 49 using Unicode, which is even worse. Okay, so basically for numeric values, the binary representation or the two's complement representation is much better than the ASCII characters or Unicode characters. So, as was discussed in the previous slide, we know that the binary notation is the better format to represent numeric value. Now, we use the example of 16 bits, right? Using the ASCII code, we can only represent 2 digitals, okay? We can only represent 2 digitals. So the largest number we can represent is 99. So with 16 bits, we can only represent number ranging from 0 to 99, okay? Because if we reach like a 100, then it requires 3 characters. Now each with 8 bits, so you need 24. You need 24 bits, okay? So now, if we use the binary notation, 16 bits can represent the range of numbers from 0 to 69,535. You know, from 16 zeros all the way to 16 ones. So 16 0 represent 0, 16 1 represent 65,535. So that's a much bigger range. So definitely the binary notation is much better than the ASCII code. Now, modern computer systems can store like a multimedia data type, such as sound, images, and videos. Now, let's first look at the representation of sound. Okay. Now, sound, by definition, is a series of compression waves. Okay. Now, sound is typically generated by mechanical vibrations such as radio loudspeakers that moves through the air or other mediums, other kind of materials. Okay. A sound is an analog signal. Sometimes we call it sound wave. Okay. Sound can be characterized by its frequency and intensity. Now, the frequency is the sound of a sound contributes to its pitch and is the rate of vibration. And the intensity is a measure of loudness or amplitude, we call it. Okay. So the high frequency means the sound is much sharp. Okay. Now, to store a sound wave or waveform, then the analog signal must first be converted into binary digitals. Okay. So this process is called analog to digital conversion. Analog to digital conversion. Okay. Now, moreover, the binary digitals can have to be converted back to their analog form in order to play them. So this is called digital to analog conversion. Okay. So basically what we do is, so we first have a sound wave, and then we're going to convert the sound wave into a digital format. And then on the destination, we convert it back to its analog sound wave. Okay. Now let's look at this diagram. This diagram represents a sound wave. Now this is the time. The horizontal axis basically represents time. Now this basically represents the amplitude. Okay. Now this is the analog one, which basically represented by some kind of continuous function. Okay. Now, how can we convert this analog sound into a digital signal. Okay. To convert an analog sound wave into a digital format, we need to use a technique called sampling. Now, here's what we're going to do. Okay, so let's assume that this is actually the analog sound wave between time 0 into 1. Let's say 1 second. Okay, and then we need to divide 1 second into a small time interval. These small time intervals are basically the same. Okay, now after actually a small time interval is reached, then we're gonna pick a sample of the amplitude. Okay, and then in the next position we're gonna pick another amplitude. Then we're gonna pick another amplitude. We call the other amplitude. Okay. So original sound wave is a continuous function, but we want to digitalize this, so we're gonna pick some sample. Okay. So then at each sample, then we record the amplitude. So this is 9. Oh, I'm sorry. This is 6, 9, 10, 8, 6, 5, 6, 8. And then how many samples we actually, select in 1 second. So it's 1, 2, 3, 4, 5, 6, 7, 8, including the, the 1. Or we can also include the 0. Okay, so it says from 0 to 8, so we pick 9 samples for 1 second. So then we're gonna actually, send the sequence of digitals. Okay, 0, 6, 9, 10, 8, 6, 5, 6, 8. Now that's the sequence of amplitude recorded within a second. Okay, and then we can continue to do this. So basically the analog sound wave basically converted into a sequence of numbers, and then we can convert each of the number, which is now represented as a decimal, but we can convert into binary sequence, right? Okay, so now with the numbers here, so the smallest number is 0, largest number is 10. So that means if we use 4 bits, then we can pretty much, store any of these amplitude in a 4-bit, actually memory space. So for example, let's pick some of the number 0. We can record it as 0, 0, 0, 0. Now what is 6? 6 is 1, 1, 0, 0. So we need to convert 6 into a binary representation. So 9 is, let's say, 1, 0, 0, 1, right? And 10 is 1, 0, 1, 0. And 8 is 1, 0, 0, 0. 6 is 0, 1, 1, 0. And 5 is, let's see, 0, 1, 0, 1. And 6 is 1, 0, 1, 1, 0. And 8 is 1, 0, 0, 0. So that's 0. That's 6, 9, 10. And 8, 6, 5, 6, 8. So you can check that each of these 4 bits can be converted into the decimal representation, and vice versa. So we can basically store these in a computer memory. Okay. So using 4 bits. Okay. Now the reason we can store this in 4 bits is because the largest amplitude is just a 10. Okay, so that we can store in the 4 bits. Now, so we basically send the sequence of 4 bits in the network, and when the receiving side receiving that sequence, now if both sides agree the format, so then the receiving side can restore this sequence into the sequence of amplitude. Okay, so then the receiving side can, recreate the kind of sound wave. Okay, so now suppose the receiving side receiving these sequence of 4-bit binary numbers. Okay, then we can easily figure out, okay, so that's the corresponding decimal sequence is 0, 6, 9, 10, 8, 6, 5, 6, 8, right? So we know that's the sequence of amplitude in 1 second. Okay, so we basically recreate these sound wave by, record these values at each sample point, okay, over here. So then we just connect these points using the straight line. Now, this is the digital sound wave. Now, let's compare this digital sound wave with the original one. Now, certainly the original one is very smooth, right? This one is not, because we only record a finite number of amplitude. So if we want to rebuild the original sound, that's not possible. We only use limited data. Okay, so that's called recreating the signal from the sampled value. Okay, now here's the question. The digital sound wave is close to the original sound wave, but it's not the same. Okay, so if we want to recreate the signal which is closer to the original sound, what should we do? Okay, let's just continue to the next. So it's kind of obvious that the digital sound is just an approximation to the original sound wave, because original sound wave was very smooth, right? But digital sound is kind of, you can see the angles over there, so it's not really that smooth. Now the question is, how accurate can the digital sound be? Okay, how can we improve the accuracy of the digital sound? Can you provide an answer? Yes, the answer is we can improve the accuracy of the digital sound by increase the number of samples. Okay, now here we use 9 samples in a second. Now how about we double these number of samples? Instead of 9 samples, we use 18 samples, or 36 samples, or 72 samples. So we just increase the number of samples in a second. Now we can imagine that the recreated digital sound will be much closer to the original sound, right? So we know that by comparing the original sound wave with the one reproduced from the sampled values, we can easily see that the more often we sample, the more accurate the reproduction. So the number of samples per second is known as the sampling rate. Okay, so we can imagine that in theory, we can make the sampled sound wave as close to the original one as possible by increasing the sampling rate. until our ears can no longer tell the difference between them, right? We can always do that. So after we actually increase the sample that we cannot tell the difference between the original one and the digital one, then it doesn't make any sense to increase the sampling rate any further, right? As we have seen that increasing the sampling rate is one way to improve the accuracy of the sound wave, right? Now, the other fact that impacts the quality of the sound is something called bit depth. Now, the bit depth is the number of bits used to encode each sample. Okay, remember in the example we use the 4 bits to represent each of the sample data, right? Remember the sequence of sample, sequence of amplitude was 1, 0, 6, 9, 10, 8, 6, 5, 6, 8, right? And we use 4 bits. Now that 4 bit is the bit depth of this sampling. Okay. So now using 4 bits, we don't lose any information, right? Because even the largest amplitude 10 can be represented using 4 bits. However, if we use 3 bits for each sample, now in that case, now what's the largest number we can represent using 3 bits? The largest number is 111. That's 7, right? So using 3 bits, the largest number we can represent is 7. But using 4 bits, the largest number we can represent is 15. Okay. So the sample value, in this case, 10, cannot be encoded correctly, as the largest value 3 bits can be represented is, actually it's not 8, it's 7. That's a mistake. So let's take a look at this. So let's look at this figure. Now this is the same example we used in the previous slides. However, the bit depth we use is 3 bits, okay, instead of 4 bits. Now, as we mentioned in the previous slide, with 3 bits, the largest number we can represent is 111, which is 7. So this is a mistake. Okay. So the largest number we can represent is 7. Okay. So even though the sequence of amplitude is 1, 6, 9, 10, 1, 6, 9, 10, 8, 6, 5, 6, 8, right? Now, we can represent 0, 6, and 6, 5, 6 using 3 bits, right? However, for 9, 10, 8, and 8, these 4 amplitude, we cannot, store the number in these 3 bits, okay? Because 7 is the largest number we can represent. So we have to cut these number and store the largest number we can represent using 3 bits. So in here, 9, 10, 8, 8 will be replaced with 7, which is the largest number we can represent using 3 bits. Okay, now this definitely going to impact the quality of the digital sound. Because using sampling, we lose some information. But now, using 3 bits, then we lose some more information. Okay, so that's the problem. Okay, so with the previous example, people may ask, now, if using the bit depth 3, we can lose some data, lose some amplitude, right? You cannot represent all the amplitude. Some of the amplitude which is too high, we have to cut them to fit into the 3 bits. Why we want to do this? We can certainly use 4 bits, right? Yes, in theory, we can always use enough bits to fit even the largest amplitude. However, in reality, if you try to represent the actual sound waves, then we have to select the bit depth because our resource is not unlimited. In certain case, we have to assume that the bit depth is limited. Okay, no matter how big the bit depth you're going to use, there's always a chance that we cannot represent some of the amplitude. Okay, for some of the music with extremely high pitch, then we may lose some of the information. Okay, now let's take a look at the example of music CD. Okay, now for the music CD we use, we basically use the sampling rate of 44,100 per second. So that means for each second of music, we can actually pick 44,100 samples. Okay, now, so that's the sampling rate. Okay, that's the sampling rate. Okay, and then for each sample, we use 32 bits per sample for stereo recording. Okay. Again, you may ask, well, can we increase the sampling rate? Yes, you can. Or can we increase the number of bits from 32 to 64, for example? Yes, we can. But all requires more storage space. Okay. Now we can actually use an example to calculate how much space we need to store certain music. Okay. Now this is a music CD. Okay. Now with MP3 music format, sometimes it's called MPEG-1 audio layer 3, so that's why it's called MP3. For MP3 format, so we use the same sampling rate of 44,100. It's the same as a music CD, but the bit depth is 16 bits. Instead of 32 bits, we use 16 bits. So the quality of MP3 is definitely worse than the music CD, or another word, the music CD has a higher quality than MP3 music. Okay. So here is an example. So we want to calculate how many megabytes does a 4-minute song using the CD music format require. Okay, now let's look at the CD music format. The CD music format uses a sample rate of 44,100 samples per second, and each sample are represented in 32 bits. Okay, to calculate the storage space used by 4-minute song, then we need to first calculate how much storage space do we need for 1 second. Okay, so let's take a look at this. So the sample rate is 44,100, right? That's just for 1 second. Now, so that's a number of samples in a second. Now, each sample requires 32 bits, right? Now, we can convert 32 bits into bytes because 1 byte equals 8 bits. So that's going to be times 4 bytes, right? So that's the total storage space we need for 1 second of music. Now we have 4 minutes, so that means we need to convert 4 minutes into the seconds. So it's actually 4 times 60. So that's 240 seconds. So the total space is going to be 44,100 times 4 times 240, because that's the storage space used for 1 second of music, and that's the total number of seconds. Okay, now this gave you the bytes. Okay, now since the number is so big, so we can actually convert bytes into kilobyte by dividing 1024. Now this is a kilobyte, and then we divide the kilobytes by 1024 again, and this gave you the megabyte, right? So now what is this number? So I just calculate this number, and I got like a 40 point, like a 375 megabyte. So about a 40 megabyte, okay, just for 4 minutes of music. So if you want to store 10, 4 minutes song, that's going to take 400 megabytes. So it's not really that small, right? Now, if we use the MP3 format, so we store the same song using MP3 format, how many megabytes does this song require? Now, there's no much difference because MP3 also use 44,100 sampling rate, but for each sample, it use 16 bits. So, which is actually 2 bytes, right? So it's a 44 times 2. That's the number of bytes, and then if we still count the total number of time, 240 seconds, then we got 440100 times 2 times 240 divided by 1024 divided by 1024. So this is actually half of this number. It's about 20. What is this? Probably 20.2, right? About 20.2 megabyte. Okay. So using the MP3 format, we can save some space, only half of the space. For the same storage space, we can store double the number of songs, right? Now this comes with the cost, because if we use 16 bits, now for some of the music which requires extremely high pitch, then maybe 16 bits is not enough to store that high pitch. We have to cut the top, so then you're going to lose some of the quality. Now that's the trade-off. Okay, so it's a trade-off. And also, if we reduce the number of samples, we reduce the sampling rate. This is gonna also reduce the quality, right? From other perspective. So that's the reason why the sampling rate is important, and also the bit depth is also important. Now, it's hard to say, which approach we're going to use. We're going to use, high bit depth or low bit depth, or we just choose, it's kind of a trade-off. We have to, pick the one. So, if you want high quality music, you need to store the music in much bigger volume, right? Because you're going to need a more bit depth and need a more sampling rate. Okay, so it's a trade-off. Okay, so the next data type we're going to talk about is the images. An image is also an analog data. An image has to be digitalized by sampling its information before we can represent and store in the binary format. Okay, the sampling process for image is called scanning. So during the scanning, an image will be represented with a two-dimensional grid of small elements, and we call these small elements pixels or picture element. The value of each pixel is encoded as a number of bits. Okay, so the collection of these encoded pixels is called the bitmap. So now here's an example of a digital image. Now if you look at the picture on the left, now this is actually the picture of Boston Harbor, and you can see the Charles River, you can see the Hancock building, and you may wonder what's so special about this picture. Actually, there's nothing special about this picture, but if you look at the picture very carefully and look at the special area I just highlighted. Now, so look at this special area, and I actually enlarged the area. Now you can actually see a whole bunch of small squares like this. Okay, each square has a unique color. Now different square may have different colors, and then if you look from distance, now the combination of these color basically make some kind of colored picture, right? Now each square represent a pixel. A digital image is also called a bit-mapped image, and the quality of a bit-mapped image depends on two key parameters. The first one is the density of the pixels, and the second one is the number of bits per pixel. Now let's take a look at the density of a pixel. Now the density of the pixel is also called the resolution. It determines how sharply the image is represented. Now look at the example in the previous slide. Remember, we highlight a small area and we zoom in that small area and we find small dots, right? Small actually squares. Now each square represents a pixel. Now if I increase the number of pixels in that fixed square area, you bet, right? The quality of the image is going to be better. Okay, so the density of the pixel sometimes is measured in dots per inch. Okay. And also in some devices, it just measures, by the number of rows and the number of columns. This is actually mostly done in the computer monitor and the TV. For example, a full high definition TV can display image of 1920 by 1080, and sometimes we call it 1080p, right? Okay, so that means the TV screen can display 1920 columns, okay, and the 1080 rows. So now, how many pixels can we find in these 1080p full high resolution TV, high definition TV? So you both basically multiply these two numbers, right? 1920 by times 1080. Okay, so that's approximately, and actually that's 2,073,600. Okay, that's the number of pixels contained in that TV screen. Okay, a 4K TV has a resolution of 3840 times 2160. So that's how we measure the resolution. Now, the other parameter we use to measure the quality of the bitmapped image is the number of bits per pixel. This is also known as bit depth. Okay. Okay. This actually basically tells how many unique colors are available in an image color palette in terms of the number of zeros and ones or bits. Okay. Now, the more bits used to represent a pixel, the more colors and the shades of the gray that can be represented. Okay. Now, in the past, when we used the black and white monitor or black and white TV, then each pixel may just need 1 bit, because each pixel can have white color or black color. So this is very simple, right? So we know that for black and white image, you can use 1 bit for each pixel, right? That 1 bit can represent 1 and 0. 1 basically means white, 0 means black, or vice versa. It doesn't matter. We only need 2 different colors. Now, for colored images, things are a little bit more complicated. Now, each pixel requires more than 1 bit of data. Now, a typical color monitor uses 3 bytes. Now, each byte equals 8 bits. So we basically use 3 bytes or 24 bits per pixel. Now, these 24-bit color encoding scheme is sometimes known as RGB. So as we can see that the RGB basically represents red, green, and blue. Now, the RGB color system is one of the most well-known color systems in the world. It is an additive color system. Now, the RGB combines these 3 base colors, red, green, and blue, to create colors we see on our TV screen, or computer monitors, or our smartphones. Okay. Now, in RGB, each color channel uses 8 bits and expressed from 0 to 255, right? Because we use total of 24 bits, so each color uses 8 bits. Now for 8 bits, how many different numbers we can represent? We can represent number from 0 to 255. Now that's for red, and for green, we can also represent different numbers from 0 to 255, and for blue, we can do the same thing, right? From 0 to 255. Okay, so if we use 0, that means for a particular color, that means it is least saturated. And if we use 255, that means most saturated. Okay. Now with the combination of all these different numbers for each color, we can represent a total of 255. I'm sorry, not 250. Sorry, I take it back. It's actually 256 times 256 times 256. Okay, so that's total of approximately 16.7 million distinct colors. Okay, now I just need to correct. This is actually 256 because the number actually starts from 0 to 255, so that's total of 256. Okay, that's my mistake. So we have discussed various different data types: the text document, the numeric values, and the voice and the images. So now let's take a look at some of the examples. Okay. Now, first example is about a text document. So let's do some of the math. Okay. Suppose a novel has 400 pages. So you have 400 pages, and each page contains 3,500 characters. Okay. So each page contains 3,500 characters. Then the total number of characters is 400, that's the number of page, plus the number of characters per page. That's 1.4 million. So if each character is encoded into the ASCII code using 8 bits, that's the Latin 1 extended ASCII code. Now, how much storage do we need to store the document? Think about this problem. Okay, we'll be back. Now, the second problem is about image. So a photographer taken using a digital camera with 6 million pixels. Okay, it's not really a high quality digital camera, right? So nowadays we can find a digital camera with like 21 million pixels or even more. And now, suppose we use 24-bit true color, okay, for 1 pixel. So then we can find out how much space we need to store the image. Okay. Now 6 million pixel, that's 6 million. Now 24 bits per pixel. So you multiply 6 million by 24, and you got 144 million bytes or bits. Okay. Now 144 million bits. How much storage do we need to store the image? Actually, for both questions, the answers the answers are very straightforward, right? So let's look at the answers for these two questions. Now the first question, we have 400 pages and each page has 3,500 characters. So we have a 1.4 million characters. Now each character use 8 bits. So that means you need a total of 1.4 million bytes, right? Because each character use 8 bits. Now 8 bits is just 1 byte, okay? So now you have 1.4 million characters. So that means 1.4 million bytes. Okay, now we can convert this into kilobytes or even megabytes. Okay, so the final answer is about 1.335 megabytes. That's nothing, right? So when we talk about the USB storage, and nowadays we're talking about 1 gigabyte or 10 gigabytes or something, much bigger than this. Okay, now let's take a look at the second question. So a 6 million pixel camera with 24-bit true color per pixel. So you have a 6 million pixel times 24 bits, and 24 bits is actually 3 bytes. Okay, so you can get a total of 144 million bits, and then typically people gonna convert the bits into bytes, right? Because that's typically the storage you actually use. So it's 144 divided by 8. That's million bytes. Okay. Let's see. 144 divided by 8. 18. What's that? 64. So it's 18 million bytes. Now, in order to convert it into kilobytes or megabytes, we need to divide 18 million by 1024 and divide by 1024 twice. Then you get megabytes. Okay, so that's approximately 18 megabytes. So not exactly the same. Now 1 million is approximately the same as 1 megabyte. But not exactly the same, because for 1 million, it's basically you can divide like 1,000, but for the the bytes you're going to divide 1024, so it's slightly different. Okay, it's a little bit smaller than 18 megabytes. So so that's actually 17.2 megabytes. Okay, so that's this. So you can see that most likely, you're going to need more storage space for images than text document. The text document, doesn't take much space. Now let's switch to another topic, the error detecting code. We know the data can be stored in a computer system as binary digitals. And when data traveling as an electronic signal through any type of medium, it always experiences some kind of situation, like loss of power or strength due to the friction, as well as some kind of noise caused by unwanted electric or electromagnetic energy. Okay, if there's a for example, certain kind of electric spike, this is going to actually create a big noise, and which eventually, cause some kind of errors in the transmitted data. Now let's take a look at an example of sending two characters, A and B. Oh, I'm sorry, A and D. So if we store the characters A and D as an 8-bit extended ASCII code, like this 8-bit binary code. Now when these code are transmitted on a medium, it will be transmitted as some kind of a square waveform, like a 0. Low means 0, high means 1. Low, 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 high. So that means there's no voltage here. There's some kind of electric voltage, 0, 0, 0, 0, 0, 1. Now on the receiving side, the signal may not look like exactly the same as original because of the noises. Okay, so on the receiving side, the signal may look like this. So if the noise is kind of small, then the signal is still readable, right? So like this, you can see, oh, I know this is 0 because it's, it's actually vibrated at the low level. And this looks like a 1. And this is 0, 0. And there's a small spike over here, but I can still see that's still 0, 0, 0. And that's 1. Okay. Now, what about during the transmission and suddenly, there's an electric spike, and then it will cause some kind of, big noise in that area. And then it's really difficult to tell what is the signal that was originally transmitted, right? Here, you may say, oh, that's 0. But what is this? It is 0 or 1. Or here, it is the signal 1, or it's just an electric spike. It's a noise, okay? So you cannot tell, right? So there are many error detecting schemes which allow people to detect whether there's error introduced during the transmission. Okay. Now, the parity checking is probably the most basic form of error detecting in data communications. Okay. Now, the idea is very simple. If you want to transmit a data like character A, so it's 0, 1, 0, 0, 0, 0, 0, 1. Now you don't know whether the receiving side is going to receive the same sequence. So what you need to do is you're going to add additional bit. It's called a parity bit. Okay. You can add the parity bit at the beginning or at the end. Either way, it should be okay. So now you're going to add on the transmission side, on the transmission side, you're going to add the value of the parity bit, either 1 or 0, depend on the type of parity checking. Now, if you use the, for example, odd parity checking, okay, so that means you need to add a bit to make the whole sequence that contains odd number of ones. Okay, so for example, in this case, the original signal is 0, 1, 0, 0, 0, 0, 0, 1. So you have 2 ones. Now, since you're going to use the odd parity checking, so you're going to add a 1 to make the total number of ones an odd number. So then you transmit this signal, which contains 9 bits, to the destination. Now, if the destination receives this signal without any error, that's okay, right? The destination actually checks the 9-bit signal and count the number of ones and find out, wow, the number of ones is an odd number. So I can say I accepted this and take the parity bit out and take this as the result, the 8-bit sequence as a result. Now let's see, what about if something goes wrong, okay, with the parity checking? So again, we use the same example. So using the odd parity checking, you add 1 for this sequence, and when you transmit to the destination, on the receiving side, there's 1 error, okay? Okay, now this is not the right bit, right? In the source side, this bit is 0, but on the receiving side, it actually switched to 1 due to the noise or electric spike or whatever. So on the receiving side, then it will check the number of ones. So it's 1, 2, 3, 4. You have 4 ones, which is an even number. And then the receiving side will know there must be an error in there, right? Because you use the odd parity checking, but I receive a sequence of 9 bits with even number of ones. So there must be error over here. Now when error occurs, the receiving side has no way to know which particular bit caused the error, or which, numbers of bits that caused the error. So it may actually has 1 error, right? Or may actually has 2 or 3 errors. You never know. But I know that there must be an error. Okay. Now using even parity, then a parity bit is added at the beginning or the end of each 8-bit set, and then assign the value 0 or 1 so that the entire resulting set has an even number of ones. So you can either use odd parity or use even parity. Either one going to work. Now we're going to discuss this even more, okay? Okay, so let's summarize the examples here. So again, we use the odd parity. So for ASCII character A, now here's the 8-bit binary sequence, okay, for ASCII character A. And that's the ASCII code for character C. Now here, the difference between this one and the one we discussed before is we put the parity bit at the beginning, not at the end. Okay, at the beginning. But that doesn't make any big difference, right? So for character A, because it contains 2 ones, that's an even number. So you need to add 1 in the parity bit to make the total number of ones an odd number. Okay. So for character C, it's a different story because the ASCII code contains 3 ones, which is an odd number. So we should not put 1 in the parity bit because otherwise this is going to make the total number the number of ones, an even number. So we put the parity bit 0. Okay. So now, once the receiving side receives the 9-bit set, it will then check the number of ones. Then it apply the parity checking. Okay, check the the number of ones. If the number for the set is odd, then the parity bit will be removed and the remaining 8 bits will be accepted and decoded as the data that was sent. Okay. So in the case of number A, we know that the original bit was 9 bits sent was 1, 0, 1, 0, 0, 0, 0, 0, 1, right? So now if the receiving side receive the correct bits, then it's just to check the number of ones and find out, well, it's an odd number, so I'm going to remove this and take this as the correct result. Okay. Now, do you see any problem with this? So we're going to discuss later. Now, even the parity checking says, oh, the number of ones is odd number. So then the result is correct. That's not exactly the truth, right? Sometimes it may not be the case. So we'll talk about this later. Okay, but using the odd parity checking, we have to accept this as a true, sequence. Okay. So the question now is, even if the bits received do pass the parity checking, does it mean that the bit patterns received were the correct ones? Right? That's the question we have. Now we know if the receiving side receive a 9-bit which contains even number of ones, like this. So now you got 4 ones. So we know that there must be some transmission error. Okay, but we cannot tell which bit has an error. Or maybe there are more bits which contains the error, like this. So you count the total number, it contains 6 ones. Then there's definitely there are some errors. Okay, actually they have total of 4 error bits. Okay, let's discuss this in more detail. Now let's look at all the different scenarios. Now the first case is probably the simplest case. So if the receiving side received the same sequence, 9-bit sequences, okay, then the parity checking gonna pass, and we remove the parity bit and take the 8 bits as the correct result, right? So we actually store and decode as character A. Everyone's happy. Okay. Now the second scenario, if 1 bit is changed, so this is going to actually eventually change the total number of ones to even number. So the parity checking going to be able to figure out, well, there's an error, right? Now, actually, not just 1 bit, even if an odd number of bits, like a 1 bit, 3 bits, or even 5 bits are changed in the transmission, then the parity bit will be incorrect. And then the parity checking will conclude that there's an error, or maybe there are some errors. So we don't accept the result. Okay. So that's a second case. Now the last case is the toughest case. Now, if an even number of bits, okay, that also include the parity bit, is altered in transmission. Okay, like this case. So 1 0 1 0 0 0 0 0 1, right? So that's a parity bit. And during the transmission, okay, an even number of bits, let's say 2 bits, are altered. Okay. Let me actually use the let's say 0 0 1 0 1 1. Now, so these 2 bits are transmitted wrong. Okay. Now, if we using the parity checking, ordered parity checking, we count the number of ones, and it's fine. So it's odd. So now, based on the parity checking, we're gonna accept this as a correct result, right? And remove these parity bit and take this as the result. Now, if we try to encode that number, definitely this number will not be encoded as character A, right? I don't know what is this number, so we can check the ASCII code table to see what this sequence of number represent. Definitely, it is not the correct answer. Now that's really the problem. So the parity checking may not be able to find out all the errors, transmission errors. Okay. So the parity bit certainly works well for case 2. In that case, the odd number of bits has been changed. Now, however, the correctness of the bit doesn't necessarily mean that there are no transmission errors as shown in case 3. Now, in case 3, if the even number of bits has been changed, then the parity bit cannot detect the error. So therefore, parity bit is an error detecting code. So, and also, when an error is detected, it cannot really tell which particular bit is corrupted or which particular bits are corrupted. If this happens, the data must be discarded entirely. So you can't have to get rid of all the 9 bits and ask the sender to retransmit the data. Now, parity bit certainly has its limitation, but however, it is still the best single bit of space could possibly do for error detection.
Okay, here are some examples. Now, the following bit patterns were originally encoded using even parity. Remember, it's even parity. So, in which of them have error definitely occurred? Okay, let's take a look. So, it's even parity. Okay. Yeah, I'm going to answer the first 2 questions, and you can actually finish up the rest of these questions. So since it's even parity, and this is the bit patterns that was received. Okay, so we need to count the number of ones. So it's 1, 2, 3, 4, 5. You have 5 ones. Since we use the even parity, so the number of ones is 5, which is odd number. So this definitely has error, right? Now in this case, the second one, you have 1, 2, 3, 4, 5, 6 ones. That's an even number. So we're going to say it's correct. Now, when the parity bit detects that there's no error, it doesn't necessarily mean there's no error, okay? It just means we think there's no error, and it's just declared as correct result. Okay. So now it's your turn. So the parity bit allows us to detect the communication errors. When error occurs, it does not provide the information needed to correct the errors. Okay. However, in some data communication applications, it is desirable to develop a scheme in which error can be not only detected, but also corrected. It sounds difficult, right? So our intuition says that this is not possible, right? Because if we don't communicate with the sender, how can I know that the error happens during the transmission? However, if the message transmitted follows some kind of rule or protocols, it is still possible to develop such an error correcting scheme. Now, the other question is, why you want to do some kind of error correcting? Now, let me actually give you an example. Suppose we want to perform a communication between the Earth and Mars. Now, typically, even when the Earth and Mars are at their closest distance, the light is still going to travel at least like a couple of minutes. Okay. So when we transmit using the any kind of electronic signal, so it would take approximately the same amount of time for the signal to transmit from Earth to Mars or from Mars to Earth. Okay. Now, if there's actually communication error, so let's say the communication between Earth and Mars is 12 minutes, and if there's a transmission error, okay, so the receiving side detects an error. Okay, so that was the message that was sent 12 minutes ago, and then the receiving side basically sent acknowledgement and also send a message saying, okay, your message was wrong, and please retransmit. That message will take approximately 12 minutes to reach the sender, right? And the sender received the message and the sender another retransmit the code. So all these messages are going to be come back and forth. You're going to take a total of 36 minutes. This is really, painful. So now what about if when the receiving side receive the messages from either from Earth or from Mars, okay, then the receiving side receive the message and detect the error. Not just to detect the error, but the receiving side can also correct the error and figure out what was supposed to be the message that was sent. Then it can save at least 24 minutes for just one single communication. So to understand how the error correcting code works, we first define a concept called a Hamming distance. Okay, Hamming is an engineer, The Hamming distance is defined between two bit patterns of equal length. Okay, you have to define the Hamming distance between two bit patterns of equal length. Okay, so for these two bit patterns of equal length, the Hamming distance is defined to be the number of positions for which the corresponding bit values are different. Okay, now let's take a look at the example. So you have two bit patterns, okay, the top one and the bottom one. So then you need to, now these two bit patterns are of the same distance, right? They both has 8 bit, both have 8 bits. So then we compare the corresponding bits. Okay, so for the leftmost bits, they're the same. Okay, now they're different. They're different. They're the same, 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 different, same. Okay, now the Hamming distance is defined to be the number of positions, okay, for which corresponding bit values are different. So these 3 are the number of positions where, you know, the corresponding bit values are different. So then we define the Hamming distance between these 2 bit patterns as a 3. Okay, so the distance is 3.
Now let's actually go further and look at the ASCII code and discuss what's the disadvantage of the ASCII code. Okay, now suppose we would like to transmit the English character A, capital A. Now this is the ASCII code for character A. Okay, now suppose one of the bit has been changed. So let's say this bit has been changed. For A, the tooth actually position has 0, but now the received pattern has 1 in tooth position. Okay, now we know there's a transmission error. However, the receiving side tried to check this pattern and find out this is also a valid ASCII code. And it is actually decoded as character C. It's a lowercase c. Okay. So that's a problem. And why this is a problem, we'll talk about this in next slide. Now, we can use parity bit and detect the potential errors, but this still doesn't solve our problem, right? We want an error correcting code. So let's check what's the problem. So the problem with the ASCII code is that all the ASCII codes are too close in terms of Hamming distances. Okay, they're too close to each other. So that means any change of bit will result in another valid character. Okay, now here's the example. Let's see. Suppose we have an English letter A. It's a lowercase a. So then by checking the ASCII table, we find out this is the ASCII code 011000001. Okay, and then we can check all the ASCII code that has the Hamming distance 1 with that character A. Okay, now we check out that this is the one, ASCII code that has a Hamming distance 1 to A. And this is another one. This is another one. And this is another one. Now let's check, for example, let's check the distance between this one, which represents a Q, and let's check the distance between A and this. So we find out this is the only distinct bit. And all the corresponding bits are the same except for this one, right? So the Hamming distance is 1. Okay, so that means if one bit is changed during the transmission, the new 8-bit pattern may still be a valid character. So the receiving side may not know. Again, as I say, if we use the parity checking, the parity checking can check out whether there might be a transmission error, but parity checking still cannot figure out which one was changed, which bits were changed. Okay. Now let's go further. So let's look at the table here. Now, instead of using the ASCII code, we try to define a new set of code. We use 10 bits and we define a new set of code and map each of the bit patterns to, some letters. Okay. Now we only pick actually 6. We only pick 6 letters and map each of the letters to one of the bit patterns in this code. Okay. Now first one A maps all 0. Now remember these are all 10 bits. And B is defined as this. Now if we look at all the bit patterns, do we find anything special? Now compare with the ASCII code. Of course, the ASCII code use 8-bit, but this one use 10 bits. But the real, difference is if you take a look at the Hamming distance between any of these 2 letters, then we will find out the distance is actually not small, right? Now let's take a look at this. The distance between A and B is 5, right? Distance between A and C is also 5 because C has 5 ones and 5 zeros, and A contains all zeros. Now distance between A and D is 5, distance between A and E is 5, and distance between A and F is 10. All the bits are different. Okay. Now let's take a look at the distance between B and C. So we will find out the distance between B and C is, let's take a look. That's B. C is 0, 1, 0, 1, 0, 1, 0, 1, 0, 1. So here's 1, 2, 3, 4. Okay. So the distance between B and C is 4. And distance between B and D, let's see, 1, 2, 3, 4, 5. Yes, it's 5. And also the distance between B and E is actually 10, right? They're all opposite. Okay. Now distance between B and F is also 5. Okay. So then look at the C and D. They're 10, right? They alternate to each other. C and E, 1, 2, 3, 4, 5, 6. 6. Okay. C and F is 5. And then D and E, 1, 2, 3, 4. Okay, D and E is 4. And D and F, 5, right? And E and F, 5. So the minimum distance between any of the 2 letters is 4. Now what does that mean? What does that mean? So with the table discussed in the previous slide, okay, we know that if we transmit any of the letters, okay, for example, we transmit the letter B. B is defined as 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. Remember that the minimum distance between any of these 2 letters is 4, right? That's the minimum Hamming distance. Now suppose we try to transmit B, right? And then the receiving side receive a sequence, a bit pattern. Now suppose one of the bit has been changed. Okay, so any of the bit, you can pick one. Let me actually pick this one. Say this one has been changed. Okay. Now the receiving side received that one, received this bit pattern. Then it just compare this bit pattern with the table. Okay, the table defined in the previous slide, and there's no match, right? Because this is actually invalid bit pattern. It's not defined. Okay. Now, so that means there must be a transmission error, right? Because the original message should be valid bit pattern, but this one is not valid. So there must be some change during the transmission. Now, how can I find out which bit has been changed? If one bit has been changed, what can we do? Yes, we can compare this bit pattern with any of the bit pattern defined in the previous table. So that means we can compare this bit pattern with A, which is 0, 0, 0, 0, 0, 0, 0, 0, 0. And then we find out, okay, so the Hamming distance is 6, right? Now this is different. This is different. So you have total of 6. Which one? This? No, not this one. Okay. So the Hamming distance is 6. So that means the receiving pattern was not A, right? Because the distance is so far away. And then we just check B, which is 0, 0, 0, 0, 0, 1, 1, 1, 1, 1. And the distance between this bit pattern that was received between B, we just compare the Hamming distance. And we find out the position over here. The bit in the received bit pattern is not the same as the corresponding bit in the B. Okay, so the Hamming distance between this one, the received pattern, and a B is 1. That's the Hamming distance. Can we make any conclusion from here? Now we can compare the received bit pattern with C, D, E, F, and then we find out none of these has actually shorter distance than 1. So that means B is the closest character or closest letter to the received pattern, even though the received pattern is invalid. Now, so we can make a conclusion that the original bit pattern that was transmitted was B. Does it make sense? Most likely, yes, right? So that's the error correcting code. So we try to define the letters, make sure the bit patterns mapped to all these letters has a very, they're not close, okay? So like in this case, the minimum Hamming distance is 4 between any of the two, bit patterns. Okay, so if one bit pattern has been changed during transmission, then we can easily, identify which was the original letter that was transmitted. Okay, so let's take a look at another example. Okay, now suppose the bit pattern received is this. Okay, so it's 111 0 0 0 0 0 0 0. It's 10 bits, right? Okay, now we compare the table. So we know that in the table, now this is actually the bit pattern for A, this is the bit pattern for B, this is for C, D, E, F. And we compare the received bit pattern with any of these. There's no match, right? Now we're going to say, well, there must be something, well, something is, happening. So there's an error in the transmitted bit pattern. Now, this is one thing, but we try to figure out what was the original letter that people tried to transmit. Okay, so we compare the bit pattern received with A. Okay, so this is 1110 all 0, and then this is all 0. So now the distance is 3, right? And I compare this with B, and we find out it's 8. And compare this bit pattern with C, and it's 6. And the received pattern with D, you got a 4. And compare the Hamming distance between the received pattern with E, you got Hamming distance 2. And then 7 for the next one. So what's your conclusion? What was most likely the original letter? You bet, right? This is probably the one. This is most likely the letter that was sent. Okay. That's another example. So the error correcting code looks great, right? But there's some drawback, or there's a limitation. Okay, in order for the error correcting code to work, we have to assume that the number of transmission errors has to be less than half of the code distances. Okay, for example, in this example, because the minimum distance, between any of the two letters is 4, right? So then the number of errors cannot exceed 2. Okay. Now here is an example. So if we try to transmit the character E, okay. Now what is character E in the table? Let's see. E is 11111 00000 in the table we just discussed in the previous slide. However, now the code that was received is this. It's 1100000000. Okay, so that means originally the letter E was transmitted, but during the transmission, now these 3 bits has been changed for whatever reason, because of the electric spike or noise or whatever. So now the receiving side actually received zeros in these 3 positions. So we actually have 3 errors. Now, if we try to use try to calculate the Hamming distance between the received code with A, B, C, D, E, or an F, we will find out that the distance between this code and A is 2, right? The distance between this one and the A is 2. The distance between this code and the B is 7. C is 1010. So C is I'm sorry, C is 010101. So you have a 0101010101. So you have a 1, 2, 3, 4, 5, Yeah, so the distance is 5 between this received code and the C is 5. Okay, now we compare distance between D and this code, E and F, and then we find out the distance between this code and A is the smallest. So based on our conclusion, so the original code should be A, right? But it's wrong because the original code is E. Why? Because the number of arrows exceeded the half of the minimal Hamming distance, which is 4. So that's a problem, and that's a limitation. Now, how can we resolve that problem? What do you think? Is there any solution for this? There is a solution. What is the solution? So we can define the, all these letters with bit patterns and make sure the minimum distance between each of these 2 bit patterns is bigger, right? Then the minimum distance is not 4, but say 8. So then if we have 3 arrows, which is still smaller than half of the minimum distance, which is 4, right? So 3 is less than 4. So if you have 3 arrows, and then the receiving side can still figure out what was the original letters. Okay, what was the original letter? Okay, so that's probably the solution. But that solution comes with a cost, because in that case, for each letter, we have to map to a bit pattern with more bits, right? Okay, so that's the trade-off. And no matter what you do, if the number of arrows is still more than half of the minimal Hamming distances, then you still cannot solve the problem. So that you cannot have a guarantee, right? Okay. So we just talked about this case. Now, if a triple arrow changed the character E into 1100000000, okay, so the receiving bit pattern is this, but the original character was E. So the Hamming distance between the E and this is actually 3, which is smaller than the Hamming distance of this bit pattern and A. So we may actually think that the original letter is A, but that's not correct, right? So you can double check that one and make sure you understand what I'm talking about here. Okay, I think that's pretty much all for module 5. So if you have any questions, please let me know. Thank you.